I'm Kurt Nelson, and I work for Uber on the mobile platform team, specifically on the Android part of it. We are, I think, slightly unique in that our Android and iOS platform teams sit next to each other. And we all work together on a daily basis. So we're able to share a bunch of stuff back and forth. And I am here to talk to you about storage and shared preferences and basically how when you design an API for an operating system, you're going to live with it for a long time, and there's a lot of things that you can do poorly and you can do well. So let's jump in. So let's first talk about designing an API for an operating system. And this isn't something that most people have done probably because they don't really let you just submit new APIs to AOSP on Garrett. I challenge you to do that and just see what happens in code review. They'll just come on and be like, you need design doc, all this, you need reviews, you need to sign these clearances, et cetera, et cetera, et cetera. You need to go through API committee, all of that. So this is something that hopefully you won't have to do on a regular basis, but it's nice to know about how you have to do it so that when you're using APIs, you kind of understand where they came from and why they are how they are. And also, when you're designing an OS API, you're really designing an immutable API that lasts decades, unfortunately. If you're working on a library or your app, you can just ship a new version or pull in the new version. If you are doing an OS API, you're stuck with what the user already has on their device. So this leads to some slightly different design considerations. And already, I would say, writing a good API for a library isn't like the easiest thing ever. But the nice thing is a library, you can rev it, you can do a V2, you can easily do a lot of different fixes. RxJava V1 to V2 is, in my opinion, a way better API. And the nice thing is that you can have V1 and V2 in your app and coexist peacefully and slowly move over to the new API. Apps pick what version they want, they bundle that, life is happy. But when you're doing operating systems, you've shipped it, and now people are going to be using your API and either raving about how great it is or complaining about how horrible it is and doing conference presentations on it for 20 years. And I say, like, Flash isn't an operating system, but it kind of is in its own way, sadly, and it still isn't dead 20 years later. And I don't think anybody here is like, ooh, I want to go use those Flash APIs in the browser. And then Unix syscalls, for example, are something that have basically never changed. Once you add a Unix syscall in, it is that way. And some of those have been in there for in the decades. So all that is to kind of scare you and say, well, maybe I shouldn't do this if I don't have to. And that's really a good thing, is that if you don't need to do something in an operating system API, don't do it in an operating system API. If you can do it with plain file I/O or classic syscalls or anything that's already there, libraries are easier and often better. Now, everything I've said so far kind of applies to generic any old operating system, whether it's Linux, Android, iOS. Now, for Android, it's a little bit more harder, I would say, than a lot of other operating systems because Android ships on consumer devices that people expect to be able to hold on to for many years, yet still run all the latest apps. I mean, when you ship an app and do an ad for it, a marketing campaign, you say works on Android. You don't say works on Android, but only these devices that you bought in the last year. Oh, and this weird one that left out this piece of hardware I need, you can't run it there. No, users want to be able to install it on anything that has the Play Store. And these devices will sit around for, the US we're a little bit shorter term. I think I would say like 2 to 3 years for the US market is a good rule of thumb. Whereas in a lot of emerging markets, people are buying brand new devices running OS versions that are 3 years old. So the Android framework is slow moving as a whole. Adding new APIs is slow. Getting them out to the ecosystem is slow. And you may say, well, what about like something like Linux that's been around forever? Linux users first of all, are Linux users, so we're special people who like breaking things and updating things and recompiling our kernels to get the new APIs. Also, though, a Linux kernel, you're generally installing it once on maybe a server and then maybe never updating it for like 2 years, but never updating the software running on it either. An interesting call out of something that is still shipping brand new from Google is Google Glass Enterprise Edition, which you can't just buy off the website. You have to have a contract to buy them. But those still ship KitKat. And those are brand new devices. So even if you are writing an app and being aggressive and trying to only support the newest things, your min SDK is probably somewhere around maybe Lollipop, best case scenario. I know in the trivia last night, the Android Studio default is still at 15 or something like that. So if you are adding a framework API, people are going to be stuck with it for 8 years at least, best case. And then also, I have this brand new API. You wrote it, you shipped it in the new version of the operating system. And now I can't use it really in most cases for another year or two because nobody has Android Pie. I mean, in this room, we're probably majority of us have Android Pie, but in the US market, once again, you're going to have to wait a year or two to be able to use these APIs. Additionally, that hardware that your API is shipping on is not, you can't ship more RAM. You can't update the hardware remotely. So that hardware is, as we said when I was doing hardware is hard. And once it's shipped, it's shipped. And also, the operating system is sitting on that piece of hardware literally on a shelf in a store waiting to be bought, versus an app where it doesn't get installed until the user presses a button, so you're going to get at least the newest version at install time. There's probably phones sitting on, Pixel 1 sitting on a shelf somewhere still with the original OS installed on them. And so your job when building these types of APIs is that you have to solve that problem, but then also solve it on behalf of all of your users for the next couple years. So, okay, I'm going to design this OS API. What are kind of some of the tenets of this design? And now these rules kind of apply for library APIs too. But so if I have a really nice API, ideally I'm going to do this really, really complicated thing, and the user is just going to be like, oh yeah, call one method, and we'll go launch a rocket ship for you. And so you want to hide as much implementation complexity from the user as possible. But if you hide too much, you'll only be able to do one use case. If you have .launch rocket ship and then the user wants to go to the moon, they might have to rewrite the whole thing. Anytime you have a failure mode, ideally you will be able to handle that for the user and hopefully recover. If the rocket ship, it fails to launch the second stage, the parachute will launch and it'll come back, and that's part of the API. You didn't have to think about that as a user. But you do still need to inform the user when you have the failure cases that you cannot handle. So if something goes really poorly and as the library you don't have enough information or you don't know what the user's intent is, you need to inform them of that failure. Another nice thing is hopefully you're not slower than just someone writing and doing this thing themselves. I think a lot of libraries suffer from this, where they have this beautiful API, they solve all your problems, they make it easy, and then they're just slower than doing it the old school way of using like java.io libraries. It needs to operate safely in a shared environment. On a phone, you have more than one app. The user expects to be able to switch apps. I know your app is the most important app ever to you, and it is your little child that you are raising and want it to get the best it can, but you do need to have it share resources with other apps on the system. And your API should ensure that it can do that. If you need thread pools or a bunch of concurrent work happening, you maybe should have a way for the user to configure where and when that work happens. In summary, you're making hard engineering decisions on behalf of your user, and your user in this case is likely across the globe in a different time zone, and you've never ever met them, and you'll only ever meet them if they file an issue on your GitHub project. So When building hardware or woodworking, measure twice, cut once. When building APIs, you have to do a lot of prep work and then still measure twice, and then you can still only cut once. Once this thing is built and shipped, it is built and shipped, for the most part, as an OS API. Okay, so talked about APIs for a bit and how to design them. Let's shift modes over to a specific type of operating system API. So you have this data and you want to persist it on the device. Let's look at kind of the tree here of some common options for storing bytes on a device. So up at the root, you have good old syscalls. So you could write some C code and move files around that way. If you want to do that, I'm proud of you. I don't want to do that. Then you have the SQLite branch, so it's more relational storage. And then over on the right, you have file storage. And all the libraries for file storage and I/O are built on the Java File API underneath, at least partially. SQLite and Room are awesome. If that fits your use case, use them. Lately, though, I've been over here on the right side of the tree looking at how to store weird little one-off objects that don't really need a full relational database. And so Square OKIO is nice if you are if you find yourself dealing with images or large files and blobs, stuff along that nature. OKIO is probably a good spot to start. Square Tape is really cool if you have transactions that you really, really need to persist to disk and then possibly replay later. So I know Square built it for taking credit cards offline and then being able to replay them online later. And then you have SharedPreferences, which is this library / OS API that's been around since V1. And a lot of people really reach for it as their default for storing key value pairs on disk. So SQLite has its place. I want to talk about it for a second, and then we're going to go back over to files. SQLite is fast, it's async, it's configurable. You can turn on stuff like write-ahead logging and configure it deeply if you know the specific read-write characteristics of your database. Those all sound great. It's like, well, let's use that every time. But you have to manually write your queries. You have to handle migrating. If your app is updated, the schema will change. It might change of your database. There's some overhead of opening handles to these. When you open it, it has to make sure, has this been migrated? By default, it doesn't support stuff like reactive, but people, of course, have built libraries on top of this. And also, if you're just storing large byte arrays or images, files, things of that nature, SQLite is not great. Room, if you're going to use SQLite, Room helps with storage there, and SQLite is built into the operating system, whereas Room is a library that's shipping. So Google can hide a lot of those problems for you and handle the differences across OS versions on your behalf. But it's not great for small values and in the critical path. So say you have an auth token that when the user opens the app, you need to, as fast as you can, use to send some sort of read request to the server to get the user's data. SQLite is probably not good for this. It needs to be really fast. It doesn't have any structure, it's just a string. You just need this auth token. And also, you want to make sure that this auth token is always saved and persisted directly to disk when you get a new one. Whereas SQLite can do write-ahead logging, so it can take time, and you can configure it around it, but really, you want this one really fast thing. So for use cases like this, a lot of people reach for shared preferences. Shared preferences is really kind of a lot of people's default, like, well, it doesn't belong in a database, and I don't want to do OKIO, so let's just use shared preferences and see what happens. And that's okay. That's it's been in the OS since API v1. Back early on, Google really kind of pushed it as the primary storage option, and it mostly works. So let's talk through the problem space of key value storage and what shared preferences is trying to solve, and then we'll evaluate shared preferences on how it actually implements this whole problem space of key value storage. So let's say we're going to reinvent shared preferences from scratch now and compare it to how it actually is. So a storage API, if you first think about it, you think of file reads and writes. Like, okay, I have some bytes and a path. I want to write them there, and then I want to read them there later. So it sounds like 2 methods, maybe a handful of parameters. So let's just come up with an ideal interface. We want to have a string and an object, and we want to be able to read that object back, given a key. Well, already we have kind of made this API way more complicated than it might need to be by using object. What is an object? How do we represent it on disk? How do we represent that object on disk across app upgrades? So I'm not talking about serialization today, and I don't want to talk about serialization because Proto is awesome and you should just use that. So we're going to talk about just storing byte arrays. So here is a storage API, and you might think, okay, this looks like it works. And I mean, this will work. It will say you could write a whole library that does storage using just this. You could save your bytes and read your bytes. But what if something goes wrong? What if the disk is full? What if this path or key that the user is using is on an external SD card, and the user, while they hit save, pops out the SD card, which unfortunately people seem to do. So you have to now add to this API an exception, and then your consumer has to handle these, whether it's often just log it and say oops, or maybe actually do a retry. Okay, so throwing exception is not great, especially if you're calling this from Kotlin, where you aren't going to have to catch that. So what shared preferences did, and what you might do, is say, okay, read, if it fails, it will return an empty byte array. And what if write fails? We'll return a Boolean that is either true or false. And this is basically what shared preferences is, or the old school .commit. Now, this is great, this works, whatever, but now let's say I want to read the same key relatively often, and maybe the key points to a relatively large file. Well, I don't want to have to load that from disk every time the user calls this API. So we need some sort of in-memory cache of these key values, a hash map maybe or something, and we need to set that up somewhere. So this is the API you might end up with, where when you start using this tool, you call an initialize method that goes in and reads all these keys in, and then has them already ready to go so that your reads are fast. And this is, again, something that shared preferences does. When you get the reference to shared prefs, it actually goes out to the disk, loads an entire file, an XML file, parses it all, and shoves it all into a hash map ready to go. So your reads and writes are going to be really fast. And then they also, when in API 9-ish, they added .apply to shared prefs, which is replacing commit, so that you end up with more of this write async without a Boolean, where they're going to write async straight to the in-memory map, and then everything else is magic and handled for you, supposedly. Read still is structured the same. You do a read, you get a byte array back. And this is what shared preferences API is today, is exactly this. But, okay, you do write async. It goes into memory, it gets saved into the hash map, but then the underlying flash storage is completely full. What should happen here? With this API, you're going to just not know what happened here. You're going to do write async. You're like, okay, all's good, it's in memory. You do the read, it's good too, because the read is coming from memory. And then your user restarts the app, and suddenly your data is gone, and you don't know why. More often, though, than even being full, I feel like, is that you have cheap flash on a lot of the Android Go phones that just will have a relatively high failure rate, and then if you were to try again, it would work, but you don't know to try again because you just said, hey, .apply, go do this for me, operating system. And the operating system tries to do it, and it fails. And if you do a read, you think you're fine because there is an in-memory cache that does have that value saved in it. Now, where this starts getting interesting and kind of saves the day is that if you have multiple writes, shared preferences will actually save your data out if it fails, as long as it succeeds once after the write was done. So this first write happens, it saves it into a map. It tries to write the whole map out to disk, that fails. You then write into another key in the map, and shared preferences takes that whole map again and writes it out again. And here, if that one works, then you kind of save the day by having an in-memory cache, and your read still works, of course, and if you restart, your reads will still be visible. And here you're just kind of getting lucky. Really, if this is working, it's because you're lucky and your failure rate is such that you can get some writes in eventually and your data is still there. Real problem, though, is if the OS kills your process or the user backgrounds your app and comes back and you only had one write or just a really, really bad day for the flash, you're going to get, who knows what you're going to get back on that read call. You might get old data, you might get no data. And what I'm trying to get across here with all these examples is that writes to mobile flash will fail. Absolutely will fail eventually. And if you have an app that's installed on millions of devices, it's going to be it's not going to be a negligible rate. And these will kind of surface up to you in weird ways as weird bugs where you assume state to have been saved and it wasn't saved. And the API you're using for storage needs to acknowledge the fact that writes to mobile flash will fail and that they will fail relatively regularly, and that as an application, if you are storing important data, needs to know that it failed so that it can often just tell the user, hey, that didn't work, try again, or maybe just try again on their behalf. Maybe there's some data it can delete to free up space, things of that nature. And most of the time, nobody's noticing this. Like, when I talk to people who are using something like shared prefs, they're like, oh, it saves my data. I'm like, yeah, most of the time it does. And when it doesn't, you probably didn't notice it, but it will fail. So why does nobody notice this? Well, most developers are using pretty new devices that have good flash and are not developing on a Xiaomi knockoff Android device that doesn't even have the Play Store that has really, really bad flash. As I said earlier, the whole store, every time there's a write, is serialized as one and fully written out, so that can mask failures. And so therefore, any successful write will persist any pending changes. And then also, if you are using .commit on your shared preferences, and in Android Pie, they added more cases where commit will return false appropriately. And as I said, you're going to fail eventually. So apply has no callback, so you're not going to find out about failures. And hopefully your data's there, and changes may or not make it to disk. So let's look at some actual source code here for this. So here is the apply method. So this is from shared preferences impl.java, and I'm pulling these all from Android Pie. This code has gotten a lot better in the last 2 or 3 years, but remember there's still old OS versions out there running your app. And so .apply immediately does this commit to memory call that sets up this memory commit result object, and then posts an async job out to this queued work magical thing, which I just found out about recently, and awaits for this to happen. So apply happens, it sets up some state here, and then we're going to go look at that enqueue disk write method that actually does things. And it's kind of big here. Yeah, you can read that, okay. So the first thing it does is it sets up a write to disk runnable, and they do a lot of tracking on how many writes are in flight and handle all of that in a lockless way. They just clone the map if there's multiple writes enqueued at a time. And if they fast path it, if you are calling commit instead of apply, they check that and use that if block there on the bottom. But all this, either way they do it, they use this queued work class, which is actually, interestingly, this global static thread pool. And this thread, and when I say global, I mean across applications. This is, remember, we're in framework code here. So they're using this one thread pool across all the applications and then queuing the work in here. This queued work object also does some tricks for you so that if you get a onDestroy call to your application, it tries to flush your work before continuing onDestroy, which is nice. There's a lot of hidden behavior in there, and I haven't even fully delved into where queued work is used all over the operating system. But just know that my goal here is that they set up a ton of async calls that are all eventually enqueued, and the writing is actually done in this thread pool outside of your app. And okay, so let's look at this actual piece of work that is enqueued on this thread somewhere out in the operating system. And you'll see here there's a lot of try-catch. And the catches, interestingly, are just log.w. So if you've done the async apply, and you happen to be watching your logcat and it fails, you'll notice. If you are not watching your logcat while your app is running, you won't know anything if you use apply. Now, that MCR disk write result value that you see set in line 22 and line 35, that is the value that if you use commit, you will see. So if you call using commit, you will know if the disk is full, or if there was an I/O exception, or if your XML was corrupted, or the file didn't exist, or what else can go wrong here. Just those three things. You'll know about it. But if you call apply, you won't know about if any of these types of failures unless you're monitoring the logcat for some reason. So the moral of the story there is if you do use commit, please check the return value. It's really, really useful. And if it's false, you should tell your user, hey, that failed, and then give them either let them try again or do something else. So there's another spot where things can go awry, and it's interesting. And here I'm actually going to go ahead and show you how I kind of look through source code to find these things. So, okay. So I tend to use something called androidxref.com. And now let me make this bigger. So Android XREF is totally not supported by Google. It's someone somewhere has a server set up where they've cloned basically all of the Android source ever and ran a tool called, it's on the footer, a tool called OpenGrok that you can set up with this server on your own if you want with any source code of any sort really, and it will allow you to search it. So I want to see, okay, what happens when you get that shared preferences object? How does it get initialized? And we're going to go ahead and look at Pi. And hopefully Android XREF is up. This site goes down all the time. And so Android has a bunch of projects inside of it, and those are essentially repos. And there's a ton of them here. You can do select all, but I know that most stuff I generally care about is in this frameworks project. And we want shared preferences. So I'm going to do shared preferences. And hey, we got the source. And it's really fast. So this is way easier than cloning down AOSP and locally searching for it, especially since cloning AOSP can take 20 minutes, since it's, I think, 25, 30 gigabytes these days. And so let's go in the shared preferences here. Oh, look, it's the interface. Okay. So this isn't going to have what I want. So let me find implementations. And if OpenGrok is happy today, wait, I should be able to hover and get, well, it does an async call that breaks all the time. So I want to find implementations of shared preferences, not the actual file. So let me go back to my search here, switch to symbol. And let's find where shared preferences is used in the framework class. So hey, there's a Kotlin extension. That's cool. Let's see. This is everywhere it's used. So luckily, I know here that it's called shared preferences impl. But you can fish around in here and use there's navigation tooling and a bunch of stuff here that generally can help you find these classes. Okay, so I now have shared preferences impl. And I want to look at how initialization works. So I'm going to use navigate, and I'm going to go to, where is it? Okay, we're here. So I have my constructor, takes in this file in this mode, and then it does this load from disk. And so one of the most interesting things I found here is that right here, every time you load a instance of shared prefs, it actually just instantiates a thread to purely load the file and XML parse once, and then the thread goes away. So if you're someone who cares about threading in your app and how many threads you have, every time you initialize shared preferences, you're going to create a whole thread just to do one load. And so in my opinion, if I were to redo this API these days, there would be a way to pass an executor when creating your shared preferences so that you could provide your own thread pool that you already have and is available for I/O. Okay, so let's go look at load from disk. Okay, so it does some locking. The other cool thing that shared prefs does do on your behalf is backup files, such that if a write fails halfway through, it will actually still have the old version of the full file there, and then the next time it opens it, it will load that backup instead of the half written out broken version. So, okay, they do some backup stuff, whatnot. Now, this is kind of interesting here. This is something that could confuse you if you were using this, and that is that if something in the map loading fails, so there's an XML pool parse here, there's a buffered input stream, there's a file input stream, there's IO util is closed, so there's a bunch of spots in here where something can go wrong. And what they do if stuff goes wrong is they just catch it, and you end up with down later, they check if the map is null, and they just initialize an empty map. So meaning if the flash just didn't read and failed to read, you'll end up with all of your preferences completely empty. And it won't tell you that it tried to load them, but it failed. And so you'll just end up blowing away the user's data. So yeah, you can look around here, and right here, if the map is null, they just instantiate a new one. And there's a bunch of fun stuff in here. You can go digging in your own time if you really like reading operating system code. And let me switch back to my slides here. Okay. So I used Android X refs to look there. So, okay, so I've shown you a bunch of code, and I know it's dense and hard to read, and I'm going through it relatively fast. But my point here is that this API contract of apply with no callback is going to eventually bite you. And it's just a fundamental problem with the way the API was designed back in the early days. And part of that is because it's called shared preferences because it was meant to just share preference or to store preferences and not to store important data. And people have started using it to store important things. And that makes me sad that this is kind of people's off-the-shelf choice for storing important data. And we need to stop doing that. We need to use all those other options we have in our toolkit for data that is important. And so, okay, you're thinking, okay, Kurt, yes, it fails. I get it, it fails. But I'm doing a cache. So what if it fails? I'll just go get it from the network again. But if you're trying to do caches correctly, there's the cache partition and your cache quota, which is all separate and allows the user to separately clear their cache. But shared preferences has no option to go use that cache partition. So if you're using shared preferences for caching, you've already put it in the wrong spot. Sorry. And you need to do it a different way, probably with OKIO and files. So, okay, what is shared preferences good for? Preferences. So for very non-critical pieces of data. If the user wants to be able to select, the user wants to select a default sort order, that if they open the app again and the sort order has changed, it's not going to impact their life, shared preferences works. It's easy. The API is kind of fire and forget. You call apply, you don't think about it. A preference, though, you don't want to use it for is something like a privacy opt-out, or any sort of Boolean that if you get it wrong could end up in someone filing a GDPR claim on you for having not forgotten them or not handled that properly. So what should you do? As I said at the beginning of the talk, if room fits your use case, use room. It's really good. Tape's good too. If you're storing authentication tokens or things where you really care about performance, just use good old Java IO file. I know when I was taking computer science classes, I did programming competitions, and I think every programming competition problem begins with, here's a file you need to read in all these lines to define the problem. And it's really not that bad, file.readAllLines, things of those nature. For authentication tokens that you're loading every app startup, that's really is a good option and might be able to get you a performance gain over shared preferences. OKIO is nice if you need a stream, partial read, seek within a file, if you have big files that you can't actually load all into memory at once, machine learning models maybe, I don't know. If you're doing anything with images, please use the image libraries that are out there. Picasso and Glide are both good. They handle caching for you. They put the caches in the right folder. They have memory caches. They have bitmap caches, all handled for you. And there is a class called atomic file in the operating system, which you might think to use for doing it handles the whole backup file for you so that a write is atomic. But if you look at the source code for atomic file, you'll see it actually has some of the same problems where atomic file.save will just logcat some errors instead of returning a failure. So you're kind of back to the same place. So yeah, that's what I have to rant about shared preferences and kind of share with you what I've discovered over the years in using it. And when I was at Google, we actually straight up banned shared preferences from our internal apps and offered a entirely different solution that was basically just .apply with a callback is how you fix this. And as I said earlier, I work on the Uber mobile platform team, and if you like this type of stuff and like platform work, our platform team is hiring. Thank you.